All right, this is the gases lecture part 2 of 3, and we just talked about several gas laws, Boyle's law, Charles' law, and Avogadro's law, that were later combined to form the ideal gas law, which is PV equals nRT. So let's talk about the ideal gas law. The ideal gas law is the equation of state for an ideal gas in the sense that it describes what the gas is doing in its current state. So it tells you this is the pressure, this is the volume for this number of moles at this temperature. And given 3 out of 4 of the variables, you can figure out what the fourth one would be, because the PV equals nRT is true for all ideal gases. Now you do have to remember that there aren't any ideal gases, which is unfortunate, but real gases are very closely approximated by the ideal gas law under most conditions. So that's why PV equals nRT is so valuable. You do have to understand about R, which is the constant that PV over NT is always equal to. So for every system, you've got PV, pressure times volume, divided by the number of moles and temperature, the 4 variables that describe that gas in that state, gives you the same value every time, kind of like Boyle's law, P1 V1 equals constant, and Charles' law, V over T equals constant. R is kind of the combination of the 3 constants that you had from Boyle and Charles and Avogadro. And they have figured out just through trial and error what the value of R is, because you can take any gas system and measure P, V, N, and T, and you'll get R every time. So the value of R, which we've discussed before, is 0.08206 when you're using atmospheres, liters, moles, and Kelvin. When you're using energy related stuff, it's the 8.3145 joules per mole kelvins. But primarily with the PV equals nRT, you're using the 0.08206. So the ideal gas law is this combination of all of the things that affect what the gas is up to. It tells you the volume of the gas, the number of particles of the gas, the temperature of the gas, and all those 3 tell you what the pressure is doing. So let's see. It's important to know the units for all of these. That pressure is atmospheres, volume is in liters, N is in moles, R is liters, atmospheres, moles, and kelvins, which is actually the combination of the 4 other guys, so that they cancel out the units. Apparently I'm tired. And you can't use other units in the ideal gas law because there's no cancellation of atmospheres divided by atmospheres, for example, like you get when you're doing Boyle's law. You can simplify the ideal gas law a little bit down to this one here, which is called the combined gas law, which is pressure, volume, and temperature. If it's a single system, that means that your moles are the same and R is always the same, so N and R cancel out. And if you rearrange it, you've got PV over T equals NR equals P2 V2 over T2. So that's this, PV over T equals PV over T. So if you've got a problem that just asks you those 3 and it doesn't really indicate how many moles there are, then you can use this formula. One thing that you have to know about ideal gases is when the assumptions are true, and we'll get into that more later, but it is important to know that low pressure and high temperatures is your best bet, because at a low pressure, I just opened a menu. Because at a low pressure, you've got large spaces between the particles, so assumption 1, which the particles don't take up much space, is true, and true-ish. And at high temperatures, the particles are moving very fast, and so they don't really have the opportunity to be attracted to each other. Whereas when it's cold, the gas is about to condense, and that's when the attractions take over and make it not true. Assumption number 2. All right, so that's the ideal gas law. Next thing is molar mass of a gas. This is pretty cool because in the lab you can figure out the identity of a mystery gas just by measuring a couple of things, because you can figure out what the molar mass of it is. So step 1, you need to get the density of the gas, which is the mass of it on the balance and the volume of it in a graduated cylinder. You can also get your pressure and temperature, which is from a barometer and a thermometer. And that will give you PV equals nRT. You can solve for N. So you'll know how many moles of gas there are. So you've got your N, and you know how many grams of gas there are. And you also know that the truth about N, the number of moles is the grams divided by the molar mass. You know N, you know grams, you can solve for molar mass. So you can find this capital M, which is actually usually italic. A capital italic M, I believe, is the symbol for molar mass. And so you can kind of stick this in, little m over big M for N, and rearrange for molar mass, and you get molar mass equals density times R times temperature divided by P, pressure. So what that means is that in the lab you can get a hunk of gas, measure its mass and volume, and measure the pressure and temperature, and you can figure out the molar mass of it. If you know the molar mass of something, it's pretty easy to figure out what its identity is. So that's kind of cool. I believe we're going to do that as a lab. So this formula, the M equals dRT over P, comes up, and you do need to know how to use it. Next thing, we kind of have a potpourri of topics here on this page, is mixtures of gases. The typical example of a mixture of a gas is air, which we breathe. Yay, hope. We've got Dalton's Law of partial pressures, where Dalton was wondering what matters when you have a mixture of gases in terms of how much pressure each one is contributing to the total pressure. And, you could think that maybe the size of the gas mattered, so maybe the molar mass or the particle size, but it actually turns out, where am I now? I'll go back down here. Oop. There I am. It turns out that the only thing that matters in terms of which gas contributes a certain amount of the total pressure is the number of moles. And that's related to Avogadro, because he was talking about how a certain number of moles causes a certain amount of pressure. So in a mixture of gases, if you've got a gas that is if you've got a gas that is 60% of the mixture, it's contributing 60% of the pressure. If you've got any gas that's contributing 10% of the pressure, it's 10% of the mixture. And that's cool because that means that the identity of the gas doesn't matter when you're talking about the pressure contributed by a particular gas in a mix. So all you got to do is just add up their pressures and you get the total pressure. Or if you know the total pressure, you can figure out, okay, well, this gas is contributing 10% of 1 atmosphere, and so that means that this gas is contributing 0.1 atmospheres of pressure. In a problem asking about this Dalton's Law of partial pressures, they are likely to make you convert from grams to moles or liters to moles, using the molar mass equality or the 22.4 liters equality. So the formula looks like this. P sub T, which is the total pressure, equals pressure 1 plus pressure 2 plus pressure 3, and then you have the ellipsis, 3 dots, because you might have a mixture of 8 different gases, carbon dioxide, carbon monoxide, nitrogen dioxide, dinitrogen monoxide, oxygen, and fluorine. It could go on and on. So however many gases there are, the first gas, the second gas, the third gas, the fourth gas, the fifth gas, you add up all their pressures, and that gives you the total pressure. It doesn't matter what unit it's in as long as they're all the same. If you're using just pressures, so that could be millimeters of mercury plus millimeters of mercury plus millimeters of mercury gives you millimeters of mercury, or atmospheres gives you atmospheres. They just have to match. But if you're going to go and use it with the rest of the ideal gas law later, PV equals nRT here, you're probably going to want to switch to atmospheres because R requires atmospheres when you do the 0.08206. Oh, a sleepy one. Okay. And then next topic, we've got the meaning of temperature. It's important to know that temperature is an average measurement. When you've got a sample of gas and all of the particles are whizzing around, temperature is saying, well, what is the average kinetic energy of a single particle in there? They're not saying that every single particle is moving at exactly the same speed with exactly the same energy. Because they're hitting things and changing directions and bonking into each other. It's like pool balls on a pool table. One of them can go really fast and hit a bunch of them and make them move slowly. And then the first ball will stop. So there's bouncing. And so it's important to know that temperature measures the average. So you might have a couple of dudes that are going really, really, really fast and a couple of dudes that are going really, really slow. And in fact, there's a graph in your book that shows the kind of curve distribution of, well, when you have this temperature, most of the particles are moving at this speed, but there are some slower and some faster. This is important because the kinetic energy, if you have taken physics, which you haven't because that's next year, kinetic energy is 1/2 mv squared. That's the formula. Kinetic energy, the unit is joules. There's mass and velocity, which is in meters per second, and I think the mass has got to be in kilograms here, but you don't have to use this formula, you just have to understand what it means. What that means is that your energy can be affected by whether you're big or small, or whether you're moving fast or slow. You can have a whole lot of kinetic energy if you are a small molecule, but you're moving really fast. Or you can have a big molecule and you're moving slowly. That could be the same. So it's kind of a balance between mass and velocity as to how much kinetic energy something has. Since temperature is the average per molecule, if you've got a lot of molecules, you have more total energy. But the individual particles can be slower or faster than that average. Here is an energy-related formula with R. So the average kinetic energy is equal to 3/2 R times temperature, which you need to remember that R, this is an energy-related formula, kinetic energy, joules. R has got to cancel out joules, so the unit has got to be joules per mole Kelvin. So it's the other value, 8.3145 joules per mole Kelvin. This doesn't come up as much as the comparing two systems version of this formula, which cuts out the constant 3/2 R and gives you kinetic energy over temperature equals kinetic energy over temperature. So that's that. Now scroll down to your questions and do them, and then come back and see if you got my answers. All right, first question, we've got, what is the volume of 16 grams of sulfur dioxide at 20 degrees Celsius and 740 torr? This is mean because it makes you convert a whole bunch of stuff. So first of all, what we have is 16 grams of sulfur dioxide, 20 degrees Celsius and 740 torr. You've got T, which is 20 degrees, but it has to be in kelvins. So we convert that by adding 273 degrees to get 293 Kelvin. We've also got pressure here with 740 torr. So that's P, and that's going to be 740 over 760. And then that will give you the answer in atmospheres. You've got to convert to atmospheres. Volume is what we're looking for. We know that R is equal to 0.08206. And N is a little bit tricky until you realize that 16 grams is sufficient to figure out how many moles there are. So sulfur dioxide, sulfur weighs 32.0, oxygen, there's 2 of them, there's another 32.0, so that's a molar mass of 64 grams per mole, and 16 grams is going to be 0.25 moles of sulfur dioxide. So that's going to give you PV equals nRT, and you're going to want to rearrange that so that V is your answer. So V equals nRT over P, which is 0.25 times 0.08206 times 293 over 740 over 760. And that gives you 6.2 liters. Bam. That is the volume. There is an example of the ideal gas law in use. Woo! Alright, question 2. A weather balloon is filled with 0.295 meters cubed of helium on the ground at 18 degrees Celsius and 756 torr. What will the volume of the balloon be at an altitude of 10 kilometers where the temperature is negative 48 degrees Celsius and the pressure is 0.14 atmospheres? That's so mean. It really is mean because look at all of those units that you have to convert. Alright, first we have volume in meters cubed, which is terrible. Which, let's convert that. Meters cubed, and that's going to be meters to centimeters, because we've got to get to centimeters cubed, and centimeters cubed to mils. And since the meters is cubed, we have to cancel it thrice, and that will give us 3 centimeters, which will give us centimeters cubed. And then you need to remember that since we're converting to liters, there's centimeters cubed in a liter, there's 1,000, and there's 100 centimeters, 100 centimeters, 100 centimeters in a meter, and that's going to give us what our answer is 295 liters. So there's V. And here we've got 18 degrees Celsius, so that's temperature. That's going to be 18 plus 273, which is 295? 295? I don't know, I can't add. Do 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 do. Seriously, brain. 291. How about that? 291, and that's in Kelvin, and we've got pressure, which is in torr, and so you've got to divide that by 760 to get atmospheres. So we've got P, V, and T. N is a good question. What you end up with is it's the same balloon, so it's the same system. So it doesn't matter how much helium is in there because the N is going to be equal in the first case and the second case. So N is constant, so we don't bother with N. And these are all V1, T1, P1. And this is going to be compared to V2, T2, and P2. So V2 is what we are looking for. T2 is 225 Kelvin because of the negative 48 degrees Celsius, and P2 is 0.14 atmospheres. So that was nice. I gave you the right unit that time. So this is the combined gas law, which is P1 V1 over T1 equals P2 V2 over T2. And that gives us this, which is 756 over 760 times 291 over, oh, no, not 291. I'm erasing with white. That's not very helpful. V1, where's my V1? It's 295. Did I just write that? 295. And the temperature is 291. And that equals P2, which is 0.14, times V2, which is V2, and that is over 225. And you solve for V2, and I won't go into the algebra of it because, come on, you guys should know it. And that is V2 equals 1620 liters. All right. Number 3, an unknown gas has a density of 7.06 grams per liter at a pressure of 1.50 atmospheres and 280 Kelvin. Calculate the molar mass of the gas. So that's D equals 7.06 grams per liter, and P equals 1.50 atmospheres, and T equals 280 K, and we're looking for M, the slanty M. And this is, right, M equals dRT over P, which is going to be 7.06. This is pretty straightforward. Why was I so nice to you? 0.08206 and 280 over 1.50, and that gives you 108 grams per mole. So the molar mass of this gas is 108 grams per mole. If you had a list of potential gases, you would be able to identify which gas it was by going, oh, that's how much that one weighs. All right, number 4. A vessel is full of air at 27 degrees Celsius and 1 atmosphere, assuming air is 79% nitrogen and 21% oxygen, the diatomic ones, by volume, which that is an assumption because there are a couple of other things in the air. But we just want to deal with 2 things because that makes the Dalton's partial pressure formula easier than using 6. Calculate the partial pressure of N2 and O2. So we have a pressure that is total 1 atmosphere. And the pressure of nitrogen is being contributed based on how much nitrogen there is, not the fact that it's nitrogen. And 79% of the pressure is due to nitrogen, and so that's going to be 0.79 atmospheres out of the 1. And P of oxygen is contributing 21% of the pressure because it's 21% of the mixture. So that's going to be out of 1 atmosphere, the remainder, 0.21 atmospheres. Because what you've got is PT equals P1 plus P2. And so that's going to be 1 equals 0.79 plus 0.21. Woo! That one was pretty easy because this number was 1. Normally you would have to do something in your calculator. All right, 5. Calculate the temperature of a mole of oxygen molecules if the internal energy is 1.16 e to the 4th joules. What we've got is looking for temperature. We know the energy is 1.16 e to the 4th joules. So we need a formula with K, E, and T, which is the kinetic energy is 3/2 RT, and that's going to be 1.16 e to the 4th equals 3/2 times your R has got to have joules in it. That's going to be 8.3145. And your temperature is, we are looking for temperature, so temperature equals 232 Kelvin. Woo! Thanks very much. Bye.